Theorem on Prime Divisibility, Theorem 1.2. Welcome, everyone. To begin today's lesson, let's take a moment to reflect on our previous discussions, where we explored the fundamental theorem of arithmetic. As you recall, this theorem is a cornerstone of number theory, stating that every composite number can be expressed as a unique product of prime numbers. Essentially, that primes are the unique building blocks of all integers. Building upon this very foundation, we are now going to introduce a critical new theorem, the theorem on prime divisibility. It is important to pay close attention here, as this theorem serves as a vital prerequisite for one of the most famous proofs in mathematics, proving the irrationality of certain numbers, such as the square root of 2. Let's dive in. Statement of the theorem. Now that we have recalled the fundamental theorem of arithmetic from our previous lesson, let's look at the formal statement of our new topic, which we will call Theorem 1.2. First, we must establish our starting condition. Let p be a prime number. This is a crucial detail, as the primality of p is what makes this theorem work. The theorem itself states, if p divides a squared, then p divides a, where a is a positive integer. To make sure this isn't just abstract symbols, let's think about it in simpler terms. If a prime number is a factor of the square of a number, it must also be a factor of the number itself. In other words, the prime factor cannot suddenly appear out of nowhere just because we squared the number. It had to have been present in the original number to begin with. We will prove exactly why this is true by breaking down the prime factors in the next few slides. Understanding the logic, the proof. Now that we have stated the theorem, you might be wondering, why is this actually true? To find the answer, we need to look under the hood and analyze the building blocks of the integer $1, which are its prime factors. Let's start with step 1, where we express $1 through prime factorization. Remember what we discussed in our very first slide regarding the fundamental theorem of arithmetic. It tells us that any positive integer $1 can be broken down and written as a unique product of prime numbers. To make this mathematically clear, let us represent the integer $1 as $1 equals p sub 1, p sub 2, all the way up to p sub n $. In this notation, p sub 1, p sub 2, through p sub n $, represent the individual prime factors that make up our number $1. Keep this structure in mind, because in the next slide, we are going to see what happens to these specific building blocks when we square the number. Understanding the logic, the proof continued. Now that we have established the prime factorization of our integer $1 in the previous step, let's move on to step 2, which is squaring the integer $1. Think about what squaring actually means. We are essentially taking that entire product of prime factors we just wrote down and multiplying it by itself. Mathematically, if we take $1 squared, it is equal to the quantity p sub 1, p sub 2, all the way to p sub n $, all raised to the power of 2. When we apply that exponent to each individual factor inside the parentheses, we get $1 squared equals p sub 1 squared, times p sub 2 squared, and so on, up to p sub n $. Squared. As we will see in the next slide, this step is crucial because it shows us exactly how the exponents of our prime factors change when we move from $1 to $1 squared. Understanding the logic, the proof continued. Now that we have squared our integer in the previous step, let's move on to step 3, where we will analyze the prime factors of a squared. Take a close look at the expression we just wrote for a squared. You'll notice something very important. The prime factors of a squared are exactly the same as the prime factors of the original number. The only difference is that they appear twice as many times. To make this clearer, let's look at a quick example. If our original number a has a factor of 3, then when we square it, a squared will have a factor of 3 squared, which is simply 3 times 3. Understanding the logic, the proof continued. Now, let's move on to step 4, where we apply the actual condition of divisibility to our logic. Remember, the starting premise of our theorem is that we have a prime number, p, which divides a squared. If we look back at our work in the previous slides, we've already broken down the prime factorization of a squared. So, if p is a factor of a squared, it logically follows that p must be one of the specific prime building blocks present in that prime factorization of a squared that we just analyzed. Understanding the logic, the proof conclusion. Now, let's bring everything together for our final step in the proof. In step 5, we reach our conclusion. Think back to what we observed in step 3. We established that the prime factors of a number squared are exactly the same as the prime factors of the original number. The only difference is that they appear more frequently. So, if we are given the condition that the prime number p is a factor of a squared, then p must be present in that list of prime factors for a squared. And since that list of prime factors is identical to the list for a, it follows logically that p must also be one of the prime factors of a. Therefore, we have proven that p divides a. To see this logic in action with actual numbers rather than just variables, let's move on to our next slide and look at an illustrative example. Illustrative example. Now, I know that the logical proof we just walked through might feel a bit abstract or theoretical. To make this concept more concrete and easier to visualize, let's step away from the variables and look at a specific numerical example. For our scenario, let's assign the value of 6 to a, and let's use the number 3 for our prime number p. As we can clearly see, 3 is indeed a prime number, which satisfies the essential condition required for our theorem to work. Illustrative example, continued. Now that we have established our values for our example, where our integer a is 6 and our prime number p is 3, let's move into the first practical step. To test the theorem, we first need to find the square of our number. So, step 1 is to calculate a squared. Since we have defined a as 6, we simply calculate 6 squared, which gives us 36. Illustrative example, continued. Now that we have calculated the square of our chosen number, let's move on to step 2, where we check if our prime number, p, actually divides this result. Looking at our specific values, we ask the question, does 3 divide 36? To find out, we simply perform the division. 36 divided by 3 equals 12. Since we get a whole number with no remainder, we can confirm that yes, 3 does indeed divide 36. Illustrative example, continued. Now, let's move on to the final step of our numerical example to see if our theory matches reality. Step 3 is to check if our prime number, p, divides our original number, a. According to the theorem we've been discussing, since we have already established that 3 divides 36, it must also divide 6. When we perform the division, 6 divided by 3 equals 2, which is a whole number. This confirms that the theorem holds true in this instance. In the next slide, I will show you the underlying prime factorization that explains exactly why this mathematical relationship works. Illustrative example, explanation. Now you might be wondering, why does this happen? What is the underlying reason for this behavior? To truly grasp the logic, let's look back at the prime factorization we used in our previous steps. If we take our value for a, which is 6, we can break it down into its prime building blocks, 2 times 3. a6 equals 2 times 3. Now, when we look at a squared, which is 36, we see the result of squaring that entire product. This gives us 2 squared times 3 squared, or, if we write it out fully, 2 times 2 multiplied by 3 times 3. Notice the pattern here. The prime factor 3 exists in the factorization of 36 only because it was already present in the factorization of 6. This perfectly illustrates the core logic of our theorem. The prime factors of the square are simply the original prime factors appearing with doubled exponents. Key takeaways. First and foremost, pay close attention to the prime requirement. It is absolutely vital to remember that this theorem only applies if p is a prime number. As we will see in a moment when we discuss common mistakes, this logic does not necessarily hold true if p is a composite number. The primeness of p is the engine that makes this theorem work. Second, let's look at the factor relationship. The fundamental logic we used in our proof relies on the fact that the prime factors of a squared number, a squared, are exactly the same as the prime factors of the original number. The only difference is that in the squared version, these factors appear with doubled exponents. Finally, let's look at the logical flow in mathematical notation. We can express the essence of Theorem 1.2 as, if p divides a squared, then it implies that p divides a in this context. The vertical bar symbol denotes divides. So, if p divides a squared, it implies p divides a. Now that we have worked through the proof and seen the numerical example, let's pause and summarize the key takeaways from this theorem to ensure you have the core concepts solidified. Keep these 3 points in mind, because in the next slide, I am going to show you a specific example of what happens when you try to apply this theorem to a composite number, which is a very common pitfall for students. Common mistakes. Now, before we wrap up, I want to highlight a very common pitfall that many students encounter. It is crucial to avoid the mistake of applying this theorem to composite numbers. You might be tempted to assume that this rule works for any number, but it simply does not. Let's look at a specific example of how this logic fails. Suppose we let p equal 4, which is a composite number, and we let it equal 6. If we calculate a squared, we get 36. Now, if we check for divisibility, we can see that 4 does indeed divide 36, because 36 divided by 4 equals 9. However, if we look back at our original number, 4 does not divide 6. So, why did the theorem fail us here? It failed because our initial condition was not met. The number 4 is not prime. This serves as a vital reminder that the theorem is strictly reserved for prime numbers. Always ensure that p is prime before you proceed with this logic. Common mistakes continued. Now, moving on to our second common mistake, which is confusing the direction of the implication. It is very important to be precise about which way the logic flows. As we have seen throughout this lesson, the theorem specifically states, if p divides a squared, then p divides a. Now, don't get confused because the reverse, or the converse, is also mathematically true. If p divides a, it will certainly divide a squared. However, I want you to focus on why this theorem is so special. The real power and the real utility of this theorem lie in its ability to allow us to move backwards, from the square, a squared, back to the original number, a. This ability to descend, from the square to the base number, is exactly what we need when we tackle more complex proofs, such as proving that the square root of 2 is irrational, which we will explore in our upcoming lessons.